So having seen the 4-bit serial in, serial out shift register, today we are going to see the all fuse shift register. Why they are calling it as all fuse? Let me just tell you that. How, which are the different types of flip flops we have or shift registers we have seen? So we have categorized them, right? We have categorized them as what? Serial in, serial out, we call them as CISO. Parallel in, parallel out, we call them as PIPO. Similarly, CIPO and PISO. What is that? Serial in, parallel out, parallel in, serial out. So all that can be designed using this particular diagram. That's why it is all fuse. You can make this work as CISO. You can at the same time make this work as the parallel in, parallel out. Anything, any of the registers that we have seen so far as categories can be implemented using just this. Okay, if you want this to work as serial in, serial out, don't give anything at this particular what place. Don't give any input in this parallel enable or okay. So preset enable, you don't give anything there. You have to give serially in and you have to take the output serially here. So then it is serial in, serial out. So without this, it is serial in, serial out, as you can see here. Yeah. In this place, they have some additional circuitry in preset pin. They have got some additional circuitry. Without that additional circuitry, it's CISO, serial in, serial out. Yeah, this is the additional circuitry we are talking about. So when they bring this additional circuitry, this can be made serial in, parallel out, serial in, serial out, parallel in, parallel out, parallel in, serial out. It can be made anything. Okay, but the shift register of our interest here is uh, this. What is it? Parallel in and parallel out. How it works as parallel in and parallel out is what we need to understand. So what is the difference between serial and parallel outputs? Anybody, can you make out that? See here, serially means it is given one after the other. See, first 0 gets in, okay, then after the second clock cycle 1 gets in, then 0 gets in the third 0, then this fourth one gets in. Understand that? So that is happening one after the other. Whereas here, all the inputs can be given at a time. Yeah, this parallel in point, wherein this preset enable is given as common input to all the NAND gates here. Understand? And when this preset enable is made one, all these data are parallelly given to these bystables. Understand this, very important. If you don't understand this NAND gate, okay, you will not understand the circuit operation. So be careful in understanding this. Everybody, what I'm saying is there are every flip-flop, okay, I'll rather be calling this bistable as flip-flop. Okay, so just get used to that term, flip-flop. So to this flip-flop, to every flip-flop, you have got this NAND gate. And where is that NAND gate connected? That NAND gate is connected in the place where we had preset pin earlier. Where is the presets here? In this place, we have that NAND gate coming, along with the bubble which is existing already. Along with this bubble, we also have a NAND gate. Understand that? So that is this. Fine. Every NAND gate input has got one bit of the input that we want to feed parallelly. So that means this has got the serial input has got 4 bits here, right? 1010. Similarly, this parallel input has got the bits D0, D1, D2, and D3. And along with these 4 data inputs, another input is connected to the preset enable pin, and that's common to all the gates here. See the pointer that I'm moving on the screen. So this is preset enable. So that is commonly connected to all the NAND gates. Remember this. Let's see what happens, or let's see when this D3, D2, D1, D0 will get into this 4 flip-flops. So that is what I need to understand. Now, I want you to answer this. There is a NAND gate. After NAND gate, we have another bubble. So what do you think this particular arrangement would act as? Which gate it would act as? Can you tell me? We have a NAND gate. After NAND gate, we have another bubble there. So what it is as good as? Anybody? Anybody? Okay, let me just put it in other way so that you can understand. What I mean is, we have NAND gate. Let me write that now. Here, they have shown us a NAND gate like this. Fine. And it's not just that NAND gate. After NAND gate, we have another bubble. Okay. So which gate do you think this is acting as? Is what I'm asking you.
AND gate.
It is working as AND gate. Okay. So this is NAND. Okay. This NAND along with NOT gate. So this should work as an AND gate. So that is what is the mechanism that they have used there. So this will become AND. Now, every flip-flop has got that arrangement. See, there is a NAND along with a bubble. There is a NAND along with the bubble. And every flip-flop has got the same arrangement. Is that okay with you? Okay, that is one observation I want you to make. Now, let's understand the AND gate in more detail. Okay, why it has been made use of in this particular circuitry is what I'm explaining you. Just see that properly. Listen to this carefully, everybody. Now, suppose one of the inputs of this AND gate, let me write that again. We have A, let's say we have A as one of the inputs, and the other input is made one always. It's always one. The other input is always one. Why I'm telling you that is here, there is preset enable, right? So that preset enable, I'll make one always one. Is that okay with you? See, that means the input of this AND gate or NAND gate with additional bubble will always be one, is what I'm telling you. So this preset enable will always be one. Okay, so I'll say that one is this. This is preset enable. Let me write that. Preset enable. So this preset enable pin is always one. So if it is one, what would be this output? Can you tell me? Anybody? If one of the inputs of AND gate is always one, what would be the output? Can you work out that? Let me just let me just give you the truth table.
Zero.
Yes.
0.
No. Just see here.
Yeah. Yes, sir.
A, B, and we have got an output Y. Let's say these are the combinations 0, 0, 0, 1, 1, 0, and 1, 1. Okay, what would be the AND gate output? So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, right? 1 and 1 is 1. Okay, now you need to catch hold of the combinations. You need to catch hold of the combinations where one of the inputs is always high. So don't you think in this combination, one of the inputs is always high? See, B is high. So when B is high, what is the output here? The other output. So that means when one of the inputs is 1, the output is always the other input. Can I say this about AND gate? Listen to this statement of mine very carefully. When one input of an AND gate is 1, the output is always the other other input. Make sense? Here, this input is high, so output is the other input. This input is high, so the output is other input. So here both are 1, 1. So if any one input is 1, the output is the other input. So that means what I can say is, if any one input is 1, then the output is the other input. Does that make sense to you all? Yes. So in that sense, can you tell me What is the output Y here?
Yeah.
Yes, that's it. So that is what is the thing that you need to understand. Is that okay with you? So here, this is the arrangement they have. NAND and NOT together they have. NAND and NOT together is as good as having the operation of or functionality of AND gate. And AND gate functionality is what? If one of the inputs is high, okay, the output is always the other input. Okay, so that is what is important to understand here. Fine. Now see here, this is preset enable, which is commonly given to all the gates as one of the inputs. But they're all inputs, and all the inputs are ones here. So this is one, this is one, this is one, and this is also one. So if one of the inputs are ones here in all the AND gates, this is AND gate. Together it is AND gate. Okay. So what would be the output? So this output would be D3, and this would be D2, this would be D1, and this would be D0. Is that understood now, everybody? Yes?
Yes, sir.
Okay. Now, if you have understood this, the next thing that you need to look at is, now, do you think all these data are being given to all the flip-flops at the same time is the question. Can you answer that now? I said this particular arrangement will bring this D3, D2, D1, D0 into the flip-flop. Okay. Now the question is, are these data bits are brought into the flip-flop at the same time? Yes, they are brought into
Yes.
all the flip-flops at the same time. Why? Because they're all there, and this preset enable is made one, and the same one is given to all the gates. Okay, that means at the same time this preset enable is being made one. So when it becomes one, it is being made one at the same time. So at the same time, all these bits will get into these flip-flops. So that means that is parallel in. Understand this? Why is this called as parallel in? Because all the flip-flops are being given to the inputs of these flip-flops at the same time. That means here the preset pin is working as the input pin. Here we take JK as input pins, right? So instead of taking this JK as input pins, we can even take this preset pin as inputs, and that is what is made possible in parallel out register, shift register. Is that understood now? Okay. Now see here, what is parallel? How can I take it parallelly out? Now see here, every flip-flop has got this clock connected to it. It's the same clock that is connected to all the flip-flops. Now, whenever there is negative edge of the clock, that means negative edge of the clock comes, okay, this Q will shift, this data will shift. Understand? And whatever data is shifted, that is tapped here at the same time. Here, earlier we used to take serially data only at this point. Here, serially out, we were taking only at this point. Now, instead of taking at this point, if you can take the data here, here, and here, what happens? So we can take parallelly out at the same time. Instead of waiting for all the bits here to come one after the other, what we can do is, okay, every time there is a negative edge of the clock, we can take these outputs parallelly out at the same time. So that's why this shift register is called as parallel out also. It's not only serial, it's not only parallel in, but it can also be parallel out if we take our data from these points. Let me just mark those points. You see, I'm talking about these points. If you can take the data from these points, okay, at the same time, without waiting for the data to come out at this point, okay, so it would become parallel out. So that is why it is called as parallel in, parallel out. They say all fuse, that means all types of shift registers can come there. Which are those? They mean CISO, they mean PIPO, they mean CIPO, and they mean PISO. I hope you understand what all these are. Okay, so all this can be made possible in this. That's why it is called as all fuse shift register. But for understanding, if you can understand serial in, serial out, you're good. If you can understand parallel in and parallel out, you can understand the other two also. Is that okay with you? Fine. So how parallel it is taken out? See, instead of waiting for it to come out serially one after the other, we tap that output here itself and we get that out. We don't wait for them to come at this point serially one after the other. All the bits are tapped at the same time at these points. That's why it's also called as parallel out. Is that okay with you, everybody? Fine. Now, after that, we shall see one more shift register that is called left shift. All the shift registers are shifting this data here 0101. If we have, they are shifting this 0101 in this particular direction because the input is being given here. If we give it here, it moves like this. Understand that? So that's right shift. If you want left shift, what we need to do, see, instead of giving your data here, okay, you try give your data onto the last flip-flop first. Here we are giving to the first flip-flop first. So that's why it moves from left to right. This is left, this is right. So left to right. You understand that? So this movement is always referred to as left to right movement. Left to right movement. So it's left to right shift. So what if you want the shift register to shift the bits in this direction? What you need to do? Then you have to give your data here. That's it. So that is what is being done here. But understand, so this is designed by having, what is the difference here? What is the difference that you're finding here compared to the other shift registers that you have seen so far? Anybody, can you make out the change here?
Gates are not used.
Yes?
Gates.
Gates, no, it's not. Gates are missing. Fine. No, compared to this, I mean, not all fuse. Compared to this, what is the difference you're finding here in this particular?
Reset.
Yes. Anybody? Let me just show you that here. Maybe let me just bring that here. I hope you're able to see this. Yeah. Yeah. Now compared to this, what is the difference you're finding here? Yeah. What is the difference between these two? See, here we have used JK flip-flop, right? Whereas here we're using D flip-flop, and there is no difference in this JK flip-flop and this D flip-flop, because in JK flip-flop, what's happening? This J is taking this data bit directly, whereas K will take that data bit having after a NOT gate. So let me just tell you, this gate, the JK flip-flop, which is shown here like this, you have J, you have K. Okay, you are directly connecting the input to J, whereas the K will have the input after the inversion. Okay, so this is Q and this is Q bar. So this is as good as this actually is equal to the D flip-flop. Understand that? So there is no much, there is no difference actually. There is no difference at all. It is just one input, okay, and the same outputs you'll have. Fine. So this is the same functionality that you get using D flip-flop. Is that okay with you? So instead of taking JK flip-flop and using this inverter, you can also use this D flip-flop. Is that okay with you? So this is using JK flip-flop, whereas this is done by using D flip-flop. Both are equally good. Both are equally good. What is better here? We do not have to use this inverter. That's something additional that you may have, you have to use in JK flip-flop, whereas that can be avoided in D flip-flop because there is just one input. Get that point? So here you have to deal with two inputs, J and K, whereas here you need to deal with just one input, that's D, other than clock, I mean, other than this clock. Is that okay with you? Fine. Now here also you have clear, here also you have preset, all that is not shown. Okay. To begin with, this clear is made. Suppose I want all the Qs to be 0, 0, zeros. Let me just write that. Q3, Q2, Q1, and Q0. I want all these to be 0, 0, 0, 0. So what you need to make in this particular design? Can you make out what needs to be done for this to be made possible? Anybody? Without rather looking at clock and D input, okay, what needs to be made to make this all zeros? All is Q3, Q2, Q1, and Q0. All of them to go zero initially. Okay, what is that I need to make in this particular diagram? We did that there also. We did that in this CISO shift register also. What did we do there? Here, we made this preset one and clear equal to 0. If you make clear equal to 0, since this is negative logic, so this 0 will become 1 here. So that means it will clear the output of this flip-flop. The same thing needs to be done here. This clear needs to be made 1 to begin with. So first step one is making CLR 0. So if it is made 0, then it is as good as giving input 1 to this clear pins. So once these input pins are given once, so that means after this inverter, if you give 1, if you give 0 here, understand I'm writing that here. If you give 0 to this clear, okay, so it would become 1 here. So these are all clears. So when they become 1, okay, so all the outputs here would become zeros, is what one should understand. Is that okay with you? So this is what is done to begin with. After that, this clear is made 1. Once the output, all the outputs would go 0, the second step is making this clear 1. So that means clear, once that is cleared, then we have to see what data comes in. See here, where is the data being given here? See, so data in is here. D0 will have the data in. You see this? So this is where the data in is. So data is given in this direction. Then the output is taken here, given to the input of the previous flip-flop. Then output of this is taken. Then this is given to the input of the previous flip-flop. Fine. Then this output is taken, given to the previous flip-flop, and the data out is taken from the first flip-flop here. So this is left shift. Is this understood now, everybody? So if you give input here and give the output of this to the input of the previous flip-flop, okay, it would become left shift registers, just that. There's no much to discuss here. It's just where you give your input and where you take your output from. Okay, so that decides actually the direction of shift. Is that okay with you? I hope you have understood that. Is that clear to everybody? Okay, now we shall go with very important topic called asynchronous counter. So till now what we have seen is shift register. Shift register is stores. It's register means it stores, REG, register. It stores. Shift register, along with storing, it also shifts. But counter counts it. Counts in means what? 0 will become 1, 1 will become 2, 2 will become 3, 3 will become 4. Since it is asynchronous counters, how many flip-flops are being used? 3 flip-flops are used. So it's a 3-bit asynchronous counter. Why it has to be called as asynchronous counter is what we shall understand now. Fine. Everybody see here, asynchronous counter. Now see, what is the difference between the clock that is applied here and the way the clock is applied here? Can you make out what is the difference now? See the clock input here. The clock input is given to only the first flip-flop here, whereas the clock to the next flip-flop is actually given from the output of the first flip-flop. So the output of the first flip-flop is what is going to be the clock to the next flip-flop, and the output here is what is going to be clock to the next flip-flop. So that means it is not the same clock that is being given to all the flip-flops here, whereas in the arrangements that we have seen so far, it's the same clock which is being given to all the flip-flops. So if the same clock is given to all the flip-flops, okay, then it is called as synchronous setup or synchronous clock, whereas it is called as asynchronous counter because not all the flip-flops are having the same clock. Is that understood now? Fine. The clock is given only to the first flip-flop. Fine. And after that, whatever outputs the first flip-flop will have, that output will be given to the next flip-flop. Clock as it becomes clock to the next flip-flop. The output of the first flip-flop is given as clock to the next flip-flop. That is output as well as it works as the clock. Similarly, when this is the clock which triggers this particular flip-flop, it will have the output, and that output will be given to the given as the clock to the next flip. It is output as well as it works as clock. So that is why it is called as asynchronous. Is that understood now? Why it is called as asynchronous? Now, how to make this work as 3-bit counter is what I'll be explaining you. Now, just lend your ears. Okay. Be very careful in what I'm explaining now. Now, can you tell me, seeing this particular clock, seeing these all clocks, do you think these clocks are negative edged or positive edged clocks? Can you make out? All the flip-flops are having the clocks there, but they are not the same clocks. They are clocks with the bubble. Let me tell you that. So that means they get triggered at negative clock edge or positive clock edge.
Negative clock edge.
Very good. So they all get triggered at negative clock edge. Okay. All the flip-flops get triggered at negative clock edge. So that's why here they have shown us the negative going clock. So this is where all the flip-flops are going to get triggered. Triggered means get activated. Understand? Now let's say that this particular clock looks like this. Everybody just see here. So let's say this is the clock that is being given to the first flip-flop. Everybody just see here. It's very interesting. You will just, if you'll be appreciating what happens with this if you understand. Okay. Now see here, this is clock that we are applying here. This is clock. Now since there is this bubble at every place here of clock, they're all negative triggered. That means here are the negative edges. Here are the negative edges. Fine. So that means every flip-flop will get triggered at the negative edge. Understand? Now, one more thing that you have to understand is here. What is happening with JK? How they are connected? What is happening with JK? Can you just see here? Don't you think JK are connected together? Yes or no? Yes or no? JK are connected together. And both JK are connected. They are short. JK pins are shorted and it's connected to logic 1. So that means what we are seeing is JK equal to 1 1 is the combination we are seeing. So what happens if JK is 1 1? Can you tell me here? What happens if jk takes the value 1 1. What's happening? It's toggling. If jk is 1 1, the output toggles. Output toggles means what? If the output is 0, it becomes 1. If it is 1, it becomes 0. So that is what is the meaning of toggling. So that means, okay, since jk is 1 1 here, okay, this implies that q should toggle. Q should toggle. Okay, now understand. To begin with, let's assume all Q naught, Q1, Q2 are having the values 0, 0, 0. Let's assume that. How we can make that? If you can short this and apply 0 to this clear pin, okay, it will clear all the outputs and it will be 0, 0, 0. And one more thing, when we are using counters, FF, this we have used, the first flip-flop we have used first. FF2 we have used last. Whereas here what's happening, see, FF0 was used as our last flip-flop. Whereas here FF0 is being used as our first flip-flop. You'll understand why it is so. Okay, so everybody just see here. Fine. So this Q0 is 0. Now, this Q0, I'm writing Q0 now. Everybody just understand this, very important. This Q0 is 0. So this Q0 is 0 only till this point. What happens after this point? Can you tell me? What happens when there is a negative edge clock and jk equal to 1 1? What should happen to this Q0? Q0 should toggle, I said. So that means what should happen?
1.
1. So at negative edge, it should become 1. Okay, and that 1 should continue to be there till the next negative edge. So when the next negative edge comes, what should happen to this Q0? Again, it should toggle because jk is 1 1. Yes or no? So again it toggles. So that means it was 1 earlier. So soon after we meet this second negative going edge, it becomes 0, and this will continue to be 0 till the next negative edge. And when it finds that next negative edge, it will become 1. Again, it finds the negative edge, it will become 0. So that means this is what is the meaning of toggling. So Q0 is toggling every time there is negative edge of the clock. So that means Q0 is toggling every time there is negative edge of neg edge, we shall say neg edge of clock. Every time there is neg edge of clock, Q0 toggles. Is this understood now, everybody?